Okay, so
Okay.
we're live now. So wait.
Okay, good morning, everyone. Welcome to the third session of the 2024 RoboLaunch Seminar Series. Today, it's my pleasure to introduce our speaker, Dr. Andreea Bobu. Andreea is an incoming assistant professor at MIT and a former research scientist at the Boston Dynamics AI Institute. She works at the intersection of robotics, mathematical human modeling, and deep learning. More specifically, she studies algorithmic human-robot interaction, focusing on how robots and humans can efficiently arrive at shared representations of their tasks for smoother and more reliable interactions. Andreea obtained her Ph.D. in electrical engineering and computer science at UC Berkeley with Professor Anca Dragan. Previously, she received her bachelor's in computer science and engineering at MIT. Now, before we start, students, Andreea is currently looking for PhD students. So if you're interested in working with her, be sure to apply to the MIT Aero Astro program by December 1st, and optionally to the MIT EECS program by December 15th. And without further ado, Andreea, I'll hand it over to you.
Thank you so much for the lovely introduction, and thanks for having me today. I'm very excited to be sharing a little bit about my work on aligning robot and human representations. So this is me in a nutshell. I develop robot algorithms that learn from people, from various forms of data from them. And I do that because I really believe that if we want robots to not just live in a vacuum, they have to be capable to adapt to the people that they interact with. And as a running example, let's imagine that this Jaco robot over here wants to carry this mug over to my colleague on the left. So the way Jaco can do this is it can generate trajectories, xi, that optimize some pre-specified reward function R. And typically in robotics, this reward function is parameterized by something called a theta parameter, a preference parameter, that encodes a trade-off between different important features phi of the task. Things like the cup orientation, the distance to the table, efficiency, and so on. And so Jaco optimizes a trajectory that's based off of a combination of all of these features in the task. So here, Jaco starts off only caring about being efficient. And as we can see, it follows the shortest path from start to goal. But then I noticed that the robot is carrying the cup way too high above the table, and I don't like that. So what I can do is I can push on it to correct it. And now the robot can use my correction to adapt to how I wanted the task to be done, and thus produce a new trajectory that this time stays closer to the table to hand the mug over to my lab mate. And so this is one example of robots adapting to people. Now, I recently finished my PhD at UC Berkeley, where my brilliant AI colleagues similarly thought about getting robots to do hard tasks for people. And as an example, here they wanted to create a robot butler that can serve wine to customers. And they came up with this. So from an AI perspective and a robotics perspective, this is an amazing feat of robotics. You have this robot that can move incredibly fast. It doesn't spill a single drop of wine, and it doesn't break the glass. So this is really, really impressive. Now, from a human user perspective, though, I don't know about you, but if this is what the robot did around me, I would be personally pretty terrified. So while the robot achieves something really technically impressive, it sort of fails to consider that a real customer, a real human, would probably be startled and not too satisfied because they would be too scared of their perception of the robot spilling or breaking the glass or hitting them, so they wouldn't have a good time. So we're seeing all this amazing progress in getting robots to work well in isolation, but we still have a gap between getting them to work around other people. And we see consequences of this gap all the time in the news. On the left, there's this news article about an Uber crash in Arizona where an autonomous car fatally hit a jaywalking pedestrian simply because it wasn't programmed to know about the wild concept of jaywalking pedestrians. It only knew about pedestrians at crosswalks. And on the right-hand side, you kind of have the flip side of this, where this time the human pilot didn't know about a new feature that was implemented into this flight control system. They couldn't understand what he was doing. They started kind of entering this tug of war where they kept pulling 26 times, the MCAS system kept pulling back, and they ultimately nosedived into the ocean. So human-robot interaction is still really hard. And to understand the reason that kind of underlines all of these failures, I like to share with you an example of failed human-human interaction. The sound is turned on, it should work, but if it doesn't work, there's subtitles.
Okay. Does this row have more quarters? Does this row have more quarters, or are they the same?
The same.
The same? Okay, now watch. Now, does this row have more quarters? Does this row have more quarters, or are they the same?
That one has more quarters.
That one has more quarters?
Yeah.
Why does that one have more quarters?
Because it's stretched out.
So here this child is clearly missing something, right? He's missing this concept of conservation of certain properties like count. It's very normal for a child this age. This takes a couple more years to develop. But without understanding this concept, the child is making the wrong inferences, meaning he's answering incorrectly. And not only that, but he's able to then explain his wrong answers using these other concepts that he knows about that are actually quite unrelated to the question. In that sense, our robots are still a little bit like little children. Let's say that this time, I actually want the robot to not carry the cup above my personal laptop. The problem is the robot has no notion of distance from laptops though. And without it, it can't learn well from my push, and even worse, it latches onto these other features, distance to table, to do its tasks. Similarly to how the child was latching to all these other concepts to answer the researcher's questions. And so, in my view, one of our biggest obstacles to successful human-robot interaction is that these representations that robots have and humans have, they're more often than not misaligned. And so in my work, I've been tackling what I call the representation alignment problem. How can the robot align its representation with that of the human that it's interacting with and learning from? And so far, we've seen a more traditional approach or more traditional solution to this problem, where we have a system designer that uses their vast domain knowledge and expertise about the task to just hand specify these feature representations phi. And then the robot can use them directly to learn how to do the task as a reward function, for example, from human input theta about the task, things like the corrections that we just saw, or language, demonstrations, and so on. There's many types of human feedback that you can use to learn this reward function. And finally, the robot optimizes this reward to produce a behavior in the world. The problem with this approach is that it does require having a human specify every single thing ahead of time, ahead of deployment, ahead of actually testing the robot. And it's pretty unreasonable to assume that the system designer can think of what any human in any task, in any environment could possibly care about a priori. So you might say there's possibly a simple solution to this. Why not just learn these feature representations as well? After all, that is the main thing that the deep learning revolution has enabled. Well, we tried that, and let's see what happened. So if the person cares about keeping the cup close to this table that we just saw and away from the laptop, spatially, we could think of the reward function as looking something like this, where it's really low in yellow when you're right above the laptop and high above the table, and it gets better the closer to the table and farther from the laptop you look. And so when the robot is missing some features, like the distance to laptops, deep learning tells us that we can just model the missing feature as a neural network, collect a few demonstrations from the person for how to do the task, so the human just shows the robot how to do it. And then you can use these demonstrations to both extract what's missing implicitly and learn the reward function kind of all at once. And this is what we get. It turns out that we vaguely learned that being around the laptop is bad, but we don't really learn this more fine-grained causal details of the reward function. Now, why is that? Well, these demonstrations of the task that we get from the person, they're meant to teach the robot just how to do the task. They're not meant to teach the robot about the features that are missing per se. And so here, the neural network is just hoping to learn about the missing feature implicitly from these demonstrations, to kind of just pick up on them along the way. But by trying to do both things at once, deep learning ends up generalizing pretty poorly. And the implication is that if I now take this reward function and optimize it, I get this pretty suboptimal behavior in contrast to how I would want to do the task. So we have one paradigm that learns good rewards, but requires this handcrafted specification of the representation. And then the other paradigm avoids direct feature specification, but does a pretty poor job generalizing. So my question is, can we somehow bridge this gap? Can we have some sort of learning involved, but recover something that's more structured and more salient? So rather than assuming a representation or hoping they'll just pick it up along the way, a core idea in my work is that robots should directly engage with humans in an interactive process for arriving at a shared representation of their task. And this has led to a divide and conquer approach to the robot learning problem. So the idea is, let's first focus explicitly on learning the representation from human input before using that representation for learning the downstream task, for doing robot learning. What's really nice about this approach is that we're not stuck with demonstrations anymore. We actually have this opportunity to design new types of human input, representation-specific input. They're explicitly targeted at teaching the representation and can do that effectively. And so in the past few years, I've studied how to formalize representation alignment and human-robot interaction through a variety of different research directions. But today, I'll share with you just a quick taste of these three directions, each of which plays a critical role in bringing this vision together. Now, I'll mostly focus on the first one for the time being, because I think it's the most exciting and the most crucial question, which is, how do we actually learn these representations from human? How do we do that? And so to dive deeper into this first part, let's come back to this example where we had what is called a deep inverse reinforcement learning, or IRL method, that modeled the missing feature as a neural network and collected some demonstrations and learned both what's missing and the reward from these demonstrations. So what if instead of trying to do both of these things at once, we applied our divide and conquer philosophy? And we first focused on just learning the feature that's missing on its own by asking the human input for some sort of mystery input about it that I'll tell you about in just a second, and only then learned the reward on top, how to do the task, from task-specific inputs like demonstrations or physical corrections that we saw before. And so that's what we're going to do. But obviously, the big question is, what is this mystery representation-specific input? We can still model the feature as a neural network, but then one simple idea for a type of representation-specific input would be to just ask the person for labels representing the feature value at different states in the state space, and then just use these labels to directly supervise the training of the neural network. So I can ask the human, what is the feature over here when I'm right above the laptop? What is the feature value over here when I'm away from the laptop? There's a couple problems with this. First, to cover the vast state space, you would need the robot would need a ton of labels from the person, which is very burdensome. These state spaces can be extremely large. Even if I discretize the space, I can have millions of states. I can't exactly ask the person for 1 million data points. But even worse, people are actually pretty imprecise when labeling states directly. A label of 0.32 doesn't exactly come natural to us. Turns out we can actually address the second problem by instead asking the person to provide relative labels, comparing the feature values in pairs of states across the space. And so then we can train this neural network with what is called the Bradley-Terry model for pairwise comparisons, and just use that model for direct supervised learning. The problem still is that we still need too many comparisons to cover the whole state space. And so our take on this problem was that humans are actually a lot more intelligent and capable than just giving us 0, 1 labels, so long as we give them the right way to give us data. And so what we wanted here was to come up with a sort of feature input that is informative for the robot, but at the same time doesn't place too much sample complexity burden on the human. And so our idea was that we can pack a lot more information if we ask the person for a sequence of states with the feature values that are monotonically decreasing along that sequence. And we call a sequence of this property a feature trace. And now the robot can automatically extract comparisons by exploiting this monotonicity in the trace. And we'll dive into this a little deeper in just a second. But first, in practice, what this looks like is if I want to teach the robot about something like distance from laptop, I can start somewhere where the feature is really highly expressed, so right above the laptop, and then move the robot monotonically towards a place where the feature is not highly expressed, so away from the laptop. Now the robot can collect a few of these traces spanning the space, and it can learn a feature function that's defined by them. And to learn this function, the robot can exploit the assumptions that it has about the feature traces. So first, we know about the monotonicity assumption. We know that feature traces satisfy monotonicity, where the feature values decrease along the states of the trace. What this means is that I can take any ordered combination of 2 states along the trace and label them as 1 because it's an ordered tuple, meaning the first state we know it's gonna have a higher feature value than the second because of this monotonicity. What's special about this property is that we end up with a number of tuples that's quadratic in the length of the trace. So for any single 1 feature trace, we end up with something along the lines of 200, 300 comparisons, which is a ton of data. The second thing we know is that we can relate feature values across traces because we know that all traces approximately start high and go low. And so what this means is that for any 2 traces, the feature values for the starts should be approximately equivalently high, and the same for the ends, where they should be equivalently low. And this gives us equivalence tuples with a label of 0, 5 that symbolizes equal preference between the states. So now we can take the data set of monotonicity tuples and equivalence tuples and incorporate them into a cross-entropy loss based on this Bradley-Terry model and train a simple multi-layer perceptron for the feature that we're missing. I'd like to now share with you some actual examples with features that we learned using feature traces from both expert users on the real Jaco and also from naive users in a user study. And for all evaluations that I'll share with you, we sampled this very large test set of 10,000 states in the robot's reachable set. So this is the 3D ball of points that you see on the left. And we colored them with the feature value. So here I'm sharing with you the laptop feature where it's yellow when you're right above the laptop, and then you go progressively towards blue as you go farther away. And for easier visualization, another thing that I can do is I can project this ball onto a 2D plane, a representative 2D plane like here. And so when we look at the ground truth distance to laptop feature, we see that there's this projected ball that decreases in intensity the farther from the laptop center we look. And when we collected traces from an expert user, we recovered a feature that looks very structurally similar to the ground truth. And this result held across 6 different features of varying complexity that we looked at. And keep in mind that the features that we trained here, they were trained with somewhere along 10 to 20 feature traces, not the thousands of demonstrations that end-to-end methods would have required. Now, we also were curious, can real users who aren't experts use these feature traces and teach robots about features? And so we did a similar thing where we asked them to teach different features. And so here they taught the distance to laptop feature. And we similarly see that users gave these traces that move away from the laptop in all directions. And so we recover a projected ball here that looks very structurally similar to what we saw on the previous slide. For distance to table, the participants cover the space vertically from up to down. And my personal favorite, what I find the coolest, is this proxemics feature, which is this notion that people really don't like having things in front of their face more so than to their sides. And so our novice users figured out that the optimum way to teach this is to give these traces that are longer in front of them and then shorter and shorter to their sides to kind of indicate this higher penalty in front of their face. And so we end up with this projected ball here that kind of looks like a half ellipsis, kind of consistent with my description of the feature. So we saw this core idea in action, but asking the humans for data is pretty expensive. So another key principle, maybe a more practical principle that has been happening in this work, is trying to learn a lot from a little. And feature traces were one example where we created data that is packed with information, but it's easy and quick to give for the person. So I'd like to share with you a few more examples of learning a lot from a little. So this will be just examples that I'm just quickly going over. I'm not going to dive deep into them. But first, we tried to extend representation learning to higher dimensional inputs like images or point clouds, which can be notoriously data hungry. And so our idea here for learning a lot from a little was to still collect a small amount of labels from the person about the feature, but then amplify these labels with simulation. So if the human wants to teach something like a near feature, objects being near each other, they can label different images as near or not near. And then we can spawn many, many different objects in the simulator to augment all of these labels into a data set of thousands of examples for free. And this enabled us to learn some pretty robust perceptual features like objects being near or above one another that can transfer to the real world without any additional human data. So here, this robot executed our feature that was completely learned in simulation. We also looked at learning more complex, fuzzy, difficult to define features like emotion. Specifically, we wanted our robot to exhibit expressive behavior, like tiptoeing to its goal when it's afraid or stomping aggressively when angry. Emotion, though, is a very subjective and thus very challenging feature to convey to our robots. But luckily, cognitive scientists have made this a little easier for us. And they found that all emotions live on this three-dimensional spectrum called valence, arousal, dominance. And because of this very nice three-dimensional structure, we're actually able to map these expressive robot behaviors in the right to this three-dimensional space with just a few labels from the person. I think in our study, each person had 20 to 30 minutes to teach this entire representation. So it wasn't really that much human effort. And as a bonus, this representation is really easy to plug into language models. So we were actually able to generalize to new expressive emotive phrases like great weather today or didn't get the offer without any new human feedback. Finally, we learned features by using common sense priors from large language models or LLMs. And here we had a human demonstrate throwing away the can in two different scenarios. And then we asked the robot, why were these two behaviors different? To us, it's pretty common sense that the human here didn't want to step on electronics, so the feature distance to electronics is something that should be important. But the robot doesn't know that. But it turns out that LLMs are actually really great at finding hidden features like this, even though the human doesn't say anything about it. It can find this out just from the description of the two different behaviors and descriptions of the scene. And so we equipped the robot with an LLM, and it was able to generalize these new unseen situations without any additional human data. So here you see we changed the electronic device, we changed the clothing material, and the robot still was able to do the task correctly, despite the fact that it's never seen these situations before. So now that we've seen how the robot can learn features one by one, how does the robot even know when its representation is misaligned in the first place? coming back to the scenario from the beginning, remember that without knowing about this feature, this robot was kind of just blindly learning to stay close to the table. I don't want this to happen. This can be very bad, especially in safety critical situations. So is there a way in which the robot can autonomously figure out that my push just refers to something that it does not know about? Well, since when people act, they don't just do so randomly, we used a model. We used the so-called Boltzmann-Noisily rational model from cognitive psychology to model people as selecting inputs in proportion to their exponentiated reward. As an aside, this model is actually a little bit of a generalization of the Bradley-Terry model that we saw before. The Bradley-Terry model was basically looking at two choices, but this model is looking at an infinity of choices as symbolized by this integral over the action space. But what's interesting about this model is this coefficient beta over here. And this coefficient models how rational or optimal the person is. Typically in robotics, this is fixed to be something reasonably high, which means that you're essentially assuming that the person is going to be reasonably rational and optimal, and thus their input should be trusted. But since we're trying to explicitly detect misalignment here, we're not going to do that. And instead, we're going to estimate this beta and reinterpret it as a confidence for how well the robot's representation can explain the human input. And we're going to do a joint inference for both the confidence and the human's preference data. What this means is that when the human and the robot are aligned, the robot will estimate a high confidence in the correct intent that explains the human's input, and thus it's going to be able to learn assuredly, learn correctly. But when they are misaligned, the robot is going to estimate a low confidence across its representation, and so it's not going to learn from inputs that it does not understand. It's going to stay robust to this. So back to this beginning example, this time when I push on the robot, it infers a low confidence, which maps to no longer incorrectly learning this incorrect behavior to stay close to the table. This behavior is not something that we hand tune. This is something that the robot does automatically. It automatically monitors its confidence in its representation, and it can learn in proportion to it, as we just saw. Or something else that it can do in safety critical situations, for example, is it can just stop execution entirely and ask for help. Now we run a user study, and when we compare the two methods in a situation where there is no misalignment, so here we have a situation where both the human and the robot know about distance to table, we see that both methods learn correctly to stay close to the table from just a few corrections from the human. So no difference here, everything works smoothly just as intended. When things get interesting, though, is when there is misalignment. So here this time, the robot doesn't know about distance to table, and instead it knows about the cup orientation. And so here the robot incorrectly learns that the human wants the cup to be tipped over. And so the human not only has to keep pushing the robot down, they also have to correct the robot's incorrect learning. So they have to keep tilting back the cup. Meanwhile, with our method, the robot is estimating this low confidence. It doesn't understand the human's input. And so it doesn't learn from inputs that it doesn't understand. It stays robust to unintended learning. Obviously, this doesn't mean that the robot miraculously knows how to stay close to the table because it hasn't learned a feature for that yet. But it's able to stay robust to misalignment. And I've kind of shared with you this framework in corrections, but there's many other types of human input that this extends to, like demonstrations or even teleoperation. And finally, to then properly learn from and interpret people's task input, the robot needs a model for how people make choices. And we just saw a model, we saw the Boltzmann model, but we actually found that this Boltzmann model was actually quite unintuitive, and a more natural model should use the human-aligned representation to adjust for any similarity that the potential trajectory choices have. I'm not diving deep into this, but what I wanted to share with you is that we ran a user study that kind of confirmed that this model is closer to how people make choices in the real world. And so this has implications beyond robotics to cognitive science and econometrics. And so when we put all of this together and look at some example reward functions that we can learn with each method, we see that this divide and conquer approach recovers much more generalizable rewards than the end-to-end baseline. This means that now the robot can do the task in the way that I wanted. It can stay close to the table, and it can also stay away from my personal laptop. Now, to close, we started by putting forward this vision of engaging with humans in this interactive process for arriving at shared representations. But this work that I've talked about has really only looked at this very standard approach, which has the human and the teacher role feeding the robot data about the representation. But in reality, seamless human-robot collaboration demands more than just this passive data absorption. This really should be a bi-directional process where the robot is an active participant in this interaction. And so I'd like to spend a couple minutes thinking about what should representation alignment look like in HRI. So I'll have a look at a few more concrete examples and challenges for the future of HRI. First, personal robots will work for and alongside humans, like this Franca cooking assistant, the Astrobee on a space station, or this TRI robot in the home. And here, representation alignment should enable the robot to easily learn new tasks from humans as the context changes, but it should also enable the robot to communicate its failure modes in a more transparent way. And this can ultimately increase the utility of the robot when supporting people, and it can also lead to more transparent failure diagnosis. In semi-autonomous driving, where we're hoping that autonomy can make the pilot or driver's life easier, we really want robots to behave according to user expectations. And if it doesn't, then it should detect that and relinquish control to the more experienced user. And this isn't specific to just experienced pilots. We really want autonomy that can adapt to users of varying levels of expertise and preferences, and do it in a way that minimizes psychological and physical human effort. So tackling these challenges will result in more trustworthy driver assistance systems, which will result in more adoption, which will ultimately reduce human burden. I also envision AVs interacting with the passengers themselves. You probably already know that Waymo has cars driving around in SF, and luckily I got to try one when I was a PhD student, and I immediately thought of the myriad of different ways in which the screen interface over here could be used to interactively learn about my own unique requirements and priorities. And so I think there's a large potential for personalization here, whether it's a grounded or a flying car. And lastly, in shared autonomy, which is meant to assist and augment human performance, robots should adapt to different changing human capabilities as the person learns more about how to teleoperate the system with time. And ultimately, this will enable more seamless and effective human-robot teams. To me, all of these exciting avenues are enabled because we're explicitly tackling representational alignment rather than just hoping it will naturally emerge on its own. I'd like to thank all of my collaborators, and I'm happy to take any questions now. Thank you.
Okay, everyone, now we're gonna go into the Q&A session. So do we first wanna go around the different team groups and each one can come line up and ask their question? And then we'll be also looking at the live chat to see if there's any questions on YouTube.
Sure. Can you hear me all right?
Yes.
Awesome. So thank you very much for the talk. That was great. So I work with Scott Neekum on reward inference, where you're trying to learn a reward function. And one of the biggest issues is that humans don't give Boltzmann rational preferences. So like either they're cyclical or there's issues with it that doesn't actually fit with this Bradley-Terry model. So my question is, if you align your representations, do you think that that's going to help you overcome this issue? Or do you think that the people are still going to be irrational regardless, I think? What do you think about that? Is this a solution to that?
Yeah, I think the aligning representations is kind of a prerequisite. You still, like, if you are taking a model-based approach to inferring or trying to figure out what the human wants or what the human's intent is, then your model still needs to better match people, or like how people make choices. We kind of had this attempt in this third part of the talk that I only briefly talked about, but I think there's a lot of insight that we can gain from cognitive science and from seeing what they have done to look at this. I know that there's been a lot of models trying to basically model human bias. Like sometimes people are myopic, sometimes people are biased towards higher reward, like higher returns, and less biased towards lower returns. So like there's all these different models of biases that you can incorporate. But I kind of think of aligning representations as a prerequisite. Like you even need the right basis function for your reward, otherwise you can't learn the correct thing at all.
Right. And the second partial question is then how do you deal with the like overwhelming diversity in humans? So I know when you're doing the things that you're doing, it's usually one human, but eventually if you scale up where you want to interact with many different people that probably have different representations that they're using, how do you actually align to the diversity of human representations?
Yeah, I mean, I kind of think of the foundation models that are starting to emerge, maybe even in robotics, as kind of a prerequisite for this. Like you can have a foundation model, but ultimately the foundation model is only going to work for the average human. Every person is unique and different, so you will need to adapt to, like my vision is that you will need to have this calibration or adaptation process where you're fine-tuning this model to the user. Now, different models have different types of biases, different humans are going to have different models that best fit the way that they're operating. So I think there's going to have to be a kind of a inference or learning process where you learn like what type of human am I dealing with. So maybe something that you can do offline is you can define many different models, many possible maybe mini foundation models. I can have, or you can think of it as personas or archetypes of humans, and you can think, oh, I have this kind of human, this kind of human, this kind of human. You're trying at inference time, you're trying to figure out what kind of human am I dealing with. Oh, I'm going to use this model for them. But still, even so, there's still going to be humans that are kind of outside of the norm. So you're still going to need to figure out quick, clever ways of adapting the closest model that you have to this user.
Awesome. All right. Thank you very much.
Hi, I'm Jessica. It's nice to meet you.
Hi, nice to meet you.
I have two questions about the feature tracing. First of all, I think it's a really cool idea. And I thought that like the progression from the I guess like human annotated labels to the like relative comparisons between them to like the feature trace is really cool. And I was curious to know, like, is that like chronologically what happened and like how you kind of arrived at that idea ultimately, like what kind of inspired the feature trace approach is like my first question.
It actually kind of is. So I was inspired by a paper from Scott Neekham's lab, actually. So there was a paper by Daniel Brown called T-Rex, where they did these trajectory rankings. So what they were doing is they were trying to learn reward functions, like the reward itself rather than the feature, but they were looking at like, let's say a batch of 5 trajectories, and they were asking the person to kind of rank them. And the idea was that gives you a lot more information, obviously, than if you just have 2 of them. So I kind of took that idea and I was thinking, what would be the equivalent in feature world, like in the state space world? So that's kind of how I arrived at the feature trace. I was like, oh, well, we can have these states that are kind of ranked. And then we're like, oh, well, what if we just have it be a trace altogether rather than ask the person to rank them?
Gotcha. Cool. Thank you. And then my second question about that is, like, is it pose agnostic? Like, let's say a laptop somewhere else, like, does it still hold up?
Yeah, so we did actually try this out. So what you need to do is you need to give traces that are diverse in the pose. Like if the laptop is always forever in the same pose at training, there's not enough information to learn that the robot should stay away from the laptop versus the robot should stay away from the specific position or pose that the laptop is at. So what we did is we gave traces where for each trace we moved the laptop a little bit. So then that is enough information to teach the robot that, oh, this should be pose agnostic. Like, don't just learn the distance from this laptop center, this specific 000 or whatever, but learn to be pose agnostic.
Great. Awesome. Thank you so much.
Hi, my name is Killian, and I just want to thank you for your presentation and also congrats on your recent assistant professor position. I actually had a general question so we're all looking into grad school options, but what about after grad school, you decided to go straight into a assistant professor position, whereas there's also postdocs and industry. You mentioned that academia positions have more flexibility in terms of research for personal areas. I was wondering, how did you decide what you want to do after your PhD?
So I think, in my view, a requirement for being faculty is that at some point in grad school, you need to feel like, wow, I really love this research and I want to keep doing it. And I feel like I'm not done. So basically, that's how I felt at some point. I'll admit that I wasn't necessarily thinking about going into faculty positions as a first-year student. I didn't know yet what I wanted to do. But around my third, fourth year, I was like, oh, I really, really enjoyed this stuff, and I don't want to stop doing it. And yeah, I had mentioned that I think in industry, you might not necessarily get to do what you were doing in your PhD. So I think that if you are someone who really loves what you're doing in your PhD, it might make more sense. You might be just very passionate about continuing that. And so it might make more sense to go into academia. Now, that there are exceptions, like it depends on your field. Like sometimes your field has more representation in industry and some other fields have less representation in industry. So it's kind of a case-by-case basis. But that was one of the main things for me. The second thing is that there is a mentorship aspect to academic jobs. I mean, there's obviously the teaching as well, so that's kind of up to you if you like teaching or not. But there's also the mentorship aspect of you get to shape students' lives for 5 to 6 years. You're like teaching people to be researchers, and that can be very satisfying if you care about that. And you don't really get that in industry, because in industry you work with people who are already shaped to be researchers. If you work with other research scientists, you still learn from each other. But yeah, it's kind of a personal thing, what you prefer.
Okay, thank you. And then in regards to the feather traces, so you have a linear line from low reward function to high reward function. How do you actually have that with multiple objects? Because I noticed for one of the plots you had in between objects. And
yeah,
if you're from here to there, how do you tell which is which?
Yeah, so the way we do that is I didn't mention this because it's too much detail for a 30-minute talk, but you actually can optionally provide the labels for the starts and the goals. Sorry, the starts and the ends. By default, they're 0 and 1. But you could, for example, say 0.7 and 0.7 if you want to give a constant trace, and you're just saying that everything in between here is the same value. So in between objects, the reward function there, the feature function was high feature value right on top of the objects, and then maybe 0.7 in between, like everywhere in between, because we wanted to teach the robot, don't go in between objects because you might collide with them or something. And so the way we did that is you give the traces for the first peak, for the second peak, you can do that 0.1, 0.1. And then you give these more equivalence traces in between where I'm saying this is 0.7 and it ends at 0.7. So all of this is the same. So that's kind of how you deal with it.
Yeah. Thank you.
Right. Hello, Professor Bobu. Thank you for your time today. My name is Gabe Nixon, third year aerospace engineering, Georgia Tech. I had one question based on your presentation today, and it was based around the core idea that you said robots should engage with humans in an interactive process for finding a shared representation. And my question is why is the default fail-safe shared representation for most cases not the human is always right? The case study I'm thinking of this is Boeing's MAX crashes due to MCAS. Was the human pilot in the right there? And what would the shared representation be for that case?
Yeah, I think the shared representation there would be for the pilot to even be aware of how the new feature works. I think in that particular case, the robot, you could think that the robot, the system, had an extra feature, so to say, but the human wasn't aware of it, or at the very least, they weren't aware how it would work, what like the actual impacts in real, like in real time would be. So I think that was the misalignment there. And I think I also gave the other example of like, what if the human designer knows everything, but the robot is missing something? And I think a lot of my talk was the robot is missing something. But I think the human can also miss something because we're designing systems in a very specific way, and we don't train people enough about them, or the person is not even an expert pilot. The person is, I don't know, some naive user in the kitchen and doesn't know what representation the robot has. And now it would be really convenient if the robot could have really natural interfaces like visualizations or language to kind of describe to the robot, to the human, what it knows and doesn't know. Another situation that I'm thinking of is, for example, you could have some partial observability, like in some cases, the human just might not be aware. Like, let's say that the robot moved the can of Coke from the fridge to my office while I was at work, and I come back and I expect to see the can of Coke in the fridge, but it's not there anymore. So, these kinds of partial observability, it's useful then for the robot to communicate to me, oh, by the way, this thing happened. The can of Coke is not in the fridge, it's in the office.
Okay, thank you.
Hello, my name's
Hi.
Elena. My peer team wanted to ask, out of all of your published works, which do you feel like had the greatest impact on like your field in human-robot interaction, and why?
Yeah, I mean, I think it was the feature traces work, because it was when I started thinking about this idea of aligning representations. Like, that was the paper after which I started thinking, wait, this is bigger than just learning one feature. This is more about alignment between humans and robots and making sure that they're kind of on the same page about like a shared language almost. I don't want to use the word language because I didn't actually do that much language work, but like a shared interface, let's say. So I think that was the most impactful in that sense. Now, I've had a stream of other papers afterwards that kind of, I think it was just a paper that kind of started the stream of feature works on this topic.
Sure. Thank you.
Hi, my name's Isaiah, and one of the questions that our group had was, particularly given the fact that neural networks are kind of a black box, and in safety critical situations, it's very difficult to figure out the ratio of like standard control theory versus the incorporation of like learned actions. So you're kind of wondering, what's your perspective on that? Like, how much do you think the ratio between like standard controls and learning should be, particularly in safety critical situations?
Yeah, so there's kind of, I have two different ways of interpreting your question. So let me give both a stab. First, there's the question of how do you handle uncertainty or misalignment if you're operating with a black box neural network. And that is really difficult. One of the primary way to quantify uncertainty with neural networks remains the ensembling method, where you just have 10 different neural networks that all predict something, and you measure disagreement. And if the disagreement is high, then you're like raising a flag. But if disagreement is low, then you're good to go. The problem is that they could all agree on the wrong thing, and you're not going to know. So then there's questions on like, oh, should we have a human in the loop, like validate some of these higher risk situations and validate that robot predictions are correct. But yeah, it's still kind of an area of still an open area of research. And the second part of the question is kind of between the mixing of when should we use classical control methods versus when should we use learning-based approaches. And I actually know that a bunch of companies do use them. Some companies use a mix of the two, because the standard control approaches, the like more classical approaches, can do certain things very well. If your assumptions, like if you have this assumption and this assumption, linear system, whatever, or linearizable system, if all of these assumptions pass, then standard approaches work very well, whereas it seems like a waste of resources to learn like a neural network policy to do that. On the other hand, there are many situations where maybe like the robot is going to be in a different situation. I don't know, maybe you have a legged robot that walks on snow, or some very irregular, like very difficult to write down standard classical equations for. And then it can be better to use learning-based approaches. So I think a lot of companies actually do switch between them, and you can have kind of a, maybe also kind of a uncertainty or kind of a confidence estimate to figure out which situation am I in. Am I in a high uncertainty, or not high uncertainty, but like high, like very regular versus very irregular situation. Based on that, use different policies.
Cool. Thank you very much.
Hello, I'm Owen. Nice to meet you. I was wondering, what thought have you given to learning representations that involve conditional preferences? So like, for example, instead of learning, hand me a cup, hand me an object instead. And then you would have some general features that would probably be the same across all objects. Like you don't want the robot to put it in your face. But then if they're handing you a book, say, you probably wouldn't mind it going over your laptop versus like a very full cup of water.
Yeah. That's actually something that we're working on right now. We're working on kind of, what are we? I think we're calling them contextual features, or so basically contextualizing feature definitions based on the environment. Exactly as you're saying, if I'm carrying, one of the examples we're looking at is if I'm carrying an empty cup of water. Like it's still a cup, but it's empty. So I shouldn't care about like orientation or about distance to laptop as much. But if the cup is half full, or I should care more. And if the cup is full to the brim, I should care even more. So okay. we are learning something right now. So stay tuned, maybe a couple more months.
Awesome. Thank you so much.
Okay, with that, we're running a bit over time, so we only have time for one of the YouTube questions. Someone's asked, how do cultural differences in behavior play into your representation learning approach, like how some cultures prefer more personal space than others?
Yeah, so that's a great question. I think one of the beauties of enabling end users, novice users, to teach their own features is that I can teach my own version of proxemics and you can teach your own version of proxemics. There could be kind of a maybe more aggregate or more foundational notion of what proxemics means, but I kind of like the fact that every person can define how big their personal space bubble should be based on their own inputs to the robot. So yeah, I think that is something that our method accounts for because we're allowing end users to give their own input of what they want.
Okay, thank you so much. And thank you to all our viewers on YouTube. We really appreciate it. Oh.
Thank you for having me.